Hi there. Welcome to this GTA video. This is the Global Training Aviation Jet-oriented course. My name's, for those who didn't assist to the previous session, my name is David Aguinaco, and I've been a ground instructor here at GTA since 2015. And I hope that this video finds you all well during these challenging and difficult days for all of us, especially for all the aviation community. Today we are going to talk about the A320 jet-oriented course flight control system, which is quite interesting system, especially because for those who never flown a fly-by-wire airplane, it's quite a big change for those students coming from the propellers of light airplanes, light aircraft, and they step up to the A320 and fly this Airbus with fly-by-wire system. Is a big change. So my goal for today, my intention is to give you a general idea about the key aspects, the key points about what's flying the fly-by-wire system and which flight loads does the Airbus 320 has, and which protections was our flight envelope during normal and abnormal conditions. So if you are ready, let's get started. So as I was saying, welcome to this A320 Airbus 320 jet orientation course, part 3, which is refers to flight controls systems. And well, as we mentioned during the previous lectures, during the previous videos, this course is designed the minimum level of acknowledgement requires commercial pilot and IFR. This course has 5 parts, 9 sections, and each video lasts about 15 minutes or 1 hour maximum. As we discussed during the previous days, we already talked about part 1, part 2, and today is quite interesting part of this course, which is flight control systems. And during the next days, you will go through the part 4, which is electrical hydraulic systems, 2 quite important systems on the A320 as well. And last but not least, the part 5, which refers to maneuvers. Well, you know, this, as we mentioned during the previous days, this virtual course is just a tool to ease your review of the required subjects on the type rating. And as I mentioned during the part 1 course, during the part 1 video, this A320 jet orientation course was designed in Global Training Aviation as a previous step before the type rating course. So our intention here is GTA is offering this course to our customers, our students, as a refreshment, just to highlight the key aspects, the key points, and the key systems of the A320. Well, Airbus 320 flight control systems. So as you can see in this slide, what we have is what's the fly-by-wire system? Well, basically the main concept is that we have the pilot can give to the will apply some inputs on the rudders or on the side stick. This input will travel through the 7 flight control computers that we have on the A320. And those 7 flight control computers will evaluate if this input is a correct input to keep the airplane flying in a safe area of our flight envelope. And then after this evaluation, these flight control computers will send this input to the hydraulic actuators, and just to move and deploy the flight control surfaces. Well, this fly-by-wire system was designed and certified to render the new generation of aircraft even more safe, cost-effective, and pleasant to fly. The flight control surfaces are electrically controlled and hydraulic actuated, But the stabilizer and rudders can be also mechanically controlled, as we will discuss on the next slides. Pilots use joystick to fly the aircraft and pitch and roll, and computers will interpret and evaluate this input if this input is safe input to keep the airplane flying enough safe flight envelope. However, when in normal load, the computers will prevent excessive maneuvers and accidents on the flight on the safe envelope in pitch and roll axis. We'll talk later about, we'll go through the which flight control loads does the A320 have. Normal, we'll talk about normal load, alternate with or without protections, direct load, or mechanical backup. So depending on the failures, on the emergencies that we are getting in our airplane in flight, depending on how which degradation mode we're getting, depending on this failure, will turn into, from a normal load, will turn into an alternate or direct load. And all these different changes on flight load will have consequences on the flight envelope. Well, the flight controls are electrically or mechanically controlled as follows. On the pitch axis, we have elevator and stabilizer. They are both electrical. On the roll axis, we have ailerons and spoilers. They are both electrical as well. On the yaw axis, we have a rudder, which is a mechanical yaw damping and turn coordination is electrical. And we have as well the speed brakes and flaps. They are both electrical. Well, this is our A320, and what we find basically regarding the flight controllers is on the forward, on the leading edge, we have fighter slats, which is leading edge surfaces. Then on the trailing edge, we have on the back side, we have the trailing edge flaps. Additionally, we have 5 spoilers as well on our top part of the wings. We'll see how these 5 spoilers work, and which they can do three functions on the in flight, which is roll control. For roll control, the A320 will use the 4 outer spoilers. For the speed brakes in flight, we'll use the airplane will use the 3 center spoilers. And once landing, during the landing roll, just for braking, the system will use all 5 spoilers for ground damping. We'll talk about this more in depth during the next slides. Well, on the back side, we have our rudder, and we have 2 elevators per side and a trimmable horizontal stabilizer. These are basically the main flight control surfaces. Well, we have 7 flight control computers which process pilot and autopilot inputs according with flight control laws. The computers are 2 ELACs for normal elevator and stabilizer and aileron control, 3 SECs for spoilers controllers, standby elevator and stabilizer control. We have 2 FACs, flight augmentation computer for electrical and rudder control. And also we have 2 flight control data concentrators, which acquire data from the ELACs and SECs and send it to the ACE instrument, electronic instrument system, and they centralize for just to get all the information from those 7 flight control computers represented in our PFD and navigation display. Well, regarding the architecture of pitch control, we find the elevators, which is 2 electrically controlled hydraulic servo jacks, which drive each elevator. And this servo jack has 3 control modes: active, damping, and centering. In normal low operation, one jack is active and the other one is acting as a damping mode. And as you can imagine, if one elevator fails, the deflection on the remaining elevator is limited in order to avoid putting excessive asymmetric loads. Well, we have as well the stabilizer, which is a screw jack driven by 2 hydraulic motors, which drives the stabilizer. The 2 hydraulic motors are controlled by one of these 3 electric motors or the mechanical trim wheel, as we see in the next slide. Well, what we define in this slide is regarding our pitch control is basically, as I was saying, was this THS trimmable horizontal stabilizer will be moved by this 2 hydraulic motors, which are controlled by 3 electric motors. And additionally, we can move this THS trimmable horizontal stabilizer using the wheel trims. Usually, when we are in ground during the ground operation, we'll set our trim wheel position, our THS, according with our center of gravity and our gross weight. Just we'll set a fixed setting on the trim wheels before takeoff. And usually when we are in flight, those trim wheels will move automatically and the THS will move automatically just to keep the center of gravity within limits. But when we need in flight, we can move as well this pitch trim, as we will discuss in the next slides. Well, regarding the elevator, as I mentioned, the elevator, we have 2 hydraulic jacks to move these surfaces. Continue with the pitch control. The electrical control in normal operation is managed by ELAC, the computer ELAC2, which controls the elevators and THS. In case the ELAC2 fails, the ELAC1 will take this control, this responsibility, this action. We have the possibility as well to of mechanical control of the THS, which is available from pitch trim wheel at any time, as I discussed, as soon as we have both green and yellow hydraulic system functioning properly. Well, this graph is quite schematic. It's quite good, and basically what it is saying is that in order to move the THS and the elevator, we have well, as I discussed, we have 3 electrical motors which control the hydraulic motor for moving the THS, and basically the main computer is the ELAC2. In case of the ELAC2 fails, the ELAC1 will take control, and so on for this SEC2 and SEC1. So THS, we do need to yellow hydraulic and green hydraulic pressure. And for the elevator, we need green hydraulic, blue hydraulic, and yellow hydraulic pressure. Additionally, if we need to move the THS, we can do it, as I mentioned on the previous slide, we can do it mechanically using the trim wheels. We can move the trim wheels both on ground or in flight. But as I mentioned, we usually do it on ground just to set the pitch trim according with our center of gravity. We usually don't touch this trim wheels in flight. Well, regarding our roll control on the A320, we have 1 aileron and 4 spoilers on each wing to control the aircraft about this roll axis. The maximum deflection of the aileron is 25 degrees, and the ailerons extend 5 degrees down when the flaps are extended, which is known aileron droop. On the electrical control for these ailerons, the ELAC1 is our main computer to manage this electrical control for the ailerons. Each aileron has 2 electrical control hydraulic servo jacks. One of these servo jacks per aileron operates at a time. Each servo jack has 2 control modes, which is active and damping mode. Well, regarding the spoilers, a servo jack positions each spoiler. The system automatically retracts the spoilers to their 0 position if it detects a fault or loses electrical control. When a spoiler of one wing fails, the symmetric one on the other wing will inhibit. Well, on this picture, this graphic, we have basically our 5 spoilers. As I mentioned in the previous slides, slide, we'll use for roll control the 4 outer spoiler, I mean spoiler 2, 3, 4, 5 for roll control in flight. And additionally, the system, the fly-by-wire system, will use as well the aileron control. The difference is that depending on the pilot input on the side stick, depending on the depending on the roll rate demanded by the pilot through the side stick control, side stick movement, the computers, the ELAC one, will evaluate these inputs, these pilot inputs, and the computers will decide if they deploy the spoilers or aileron to perform this roll turn. Additionally, the system will use the 3 center spoilers, 2, 3, and 4 for speed brakes, and we will discuss in the next part of the presentation. And the fly-by-wire system will use all spoilers from 1, 2, 3, 4, and 5 for roll, for ground roll control once landed. We will discuss the difference between landing and takeoff with a spoilers arm or disarm. We'll talk about this difference on the next part of the presentation. But roughly, this is big picture. This is how this fly-by-wire system works regarding the roll control. Well, what about yaw control? Well, we have one rudder surface control this yaw movement. Electrical rudder control, which is for yaw damping and turn coordination. This function is fully automatic, and the ELAC's computer yaw orders for coordinating turn and yaw damping, then transmit this order to the FAC. So the pilot apply a side stick input demanding a bank angle turn, and this side stick input will travel through the ELAC. The ELAC will pass the information to the FAC, to the flight augmentation computer, and will evaluate how much and which how many degrees will move the rudder just for manage and ensure this yaw damping and chair coordination. Well, additionally, we have the rudder travel limit, which is the maximum rudder travel deflection gradually reduces as the speed increases, just to avoid the structural loads. And the available rudder deflection provides sufficient yaw control within the entire flight envelope. This includes the case of maximum asymmetry thrust. Rudder trim. Well, this is quite important as well, especially when we are flying in manual flight with autopilot disconnected. We have the opportunity to trim our rudder using this electrical rudder trim. In manual flight, the pilot can apply rudder trim by the rotary rudder trim switch on the pedestal. Remember that this is quite important. With the autopilot engaged, with the autopilot on, this rudder trim rotary switch and the rudder trim reset push button are not active. So regarding our yaw control, basically the pilot will apply side stick input, performing a bank angle turn, and this input will travel to the ELAC, and the ELAC will send the information to the FAC just to yaw damping and turn coordination. The FAC will be in charge of performing the rudder travel limit and yaw damping turn coordination, and will move the rudder using the three hydraulic servo jacks. Additionally, we have the option, the possibility to move this rudder using the rudder. This will be a mechanical control on the rudder. Remember that on the A320, we usually use the rudder on ground during the ground operation, just for keep the aircraft centering on the centering on the runway center line during the takeoff. But in flight, we almost never use the rudder since we have this turn coordination and yaw damping. So on the A320, it's not necessary to use the rudder in flight, because since we have the FAC1 and FAC2 computer will manage this yaw damping and turn coordination. Well, additionally, we have the rudder trim, which is an electrical knob, remember that this we have the possibility to trim our rudder position as soon as we are flying in manual mode with autopilot disconnected. Especially, we use this rudder trim, especially when we are performing the engine failure during takeoff after B1 scenario profile, since we are getting some asymmetry in the thrust power, and we need to. We are still flying with autopilot off, and we need to center and remove this yaw moment. Well, we will need to use this rudder trim position, this rudder trim knob. Remember that the rudder trim is electrical, and you just have to keep straight this rudder trim to the nose left or nose right during usually 8 to 10 seconds, depending on which yaw moment we are getting. So we don't need to do some clicks several times. Just keep pressing the seconds that you need, and you will get the indication, the digital indication on this display will indicate how much rudder trim you're using. Well, additionally, we have in the same panel, the same rudder trim panel, we have the reset push button, which is basically, we usually this push button on ground just to reset this rudder trim position, rudder trim movement. As soon as you press this reset push button, the rudder surface will swap into the neutral, to the 0 degrees deflection. Well, what about speed control? This is quite interesting. The pilot control the speed brakes with a speed brake level. As I mentioned on the previous slide, we will use for speed brakes the spoilers, the 3 center spoilers 2, 3, and 4. The speed brake extension is inhibited mainly if the angle of attack protection is active. We'll talk about this protection. When the flaps are in configuration full for the A320 and config 3, flaps 3 for A321, or when the thrust levers are above maximum continuous thrust position, MCT, or when the alpha floor protection is activated. If an inhibition occurs when the speed brakes are extended, the speed brakes will retract automatically and stay retracted until the inhibition condition disappears. When a speed brake surface on one wing fails, the symmetric one is will be inhibited as well, just to prevent this asymmetry between both wings. The maximum speed brake deflection achievable with the autopilot engaged is obtained by setting the speed brake level to the half position, halfway. This is quite important when, remember always, you will practice this during the type rating course. As soon as when we are flying with autopilot engaged, autopilot on, the maximum speed brake deflection will be to the half position, even if the pilot take the speed brake level to the full deflection, the speed brakes will deploy only to half position. If we need to, for example, increase our rate of descent, and we need to deploy spoilers, these speed brakes to the full extended position, well, in that case, we will need to disconnect the autopilot and take the speed brake lever to the full position. Well, on setting the position of the speed brake level from half to full, no increase in speed brake deflection will be achieved, as I mentioned. Well, this refers to when we are referring. This is our speed brake handle. We have a retracted half position and full position. We will use for the speed brake control, remember the 3 center spoilers, which is 2, 3, and 4. And remember that if we are flying with autopilot engaged, autopilot on, even the pilot take the speed brake lever to the full position, the speed brake surfaces will deploy only to the half position. So if you need to extend it to the full position, you will need to disconnect autopilot off. Well, ground spoiler control, this is quite interesting as well. Spoilers, in this case, the fly-by-wire system, the airplane will use the 5 spoilers, 1 to 5. Arming, well, what's the difference between those next points, arming and full extension in case of reactive takeoff and full extension landing phase? as a summary of this slide, what's the difference between takeoff or landing with spoilers arm or disarm? I mean, the question is, can we take off with spoilers disarm? The answer is yes, we can, but the difference is that, well, in case of re-entry takeoff, in case of abandoned takeoff, we are during the takeoff roll and we get whatever failure on the icon, and we are below V1 speed, and we take the decision to abandon, to stop the takeoff. Well, as soon as we are above 72 knots, if we are taking off with a spoiler disarm, which is the non-standard procedure, for these spoiler extensions above 72 knots, the pilot will need to select one of the two reverses on the thrust levers just to make these spoilers deploy. However, if we are taking off with a spoilers arm, which is the standard procedures, I mean, pull the spoilers, the speed brake lever up, that's arming the spoilers. Well, in case of re-entry takeoff with the spoilers arm, the spoilers will deploy, will extend if we are above 72 knots, as soon as the pilot take the thrust levers back to idle. So in that case, the pilot doesn't need to select reverses for deploy for this spoiler extension. That's the main difference. Same for landing. Can we land with the spoilers disarm? Yes, we can, but that's a non-standard procedure. I mean, for landing, the standard procedure is arm the spoilers. I mean, pull this lever up. So once main gear touch down, as soon as the pilot take the thrust levers back to the idle position, the thrust, well, the spoilers surfaces will deploy just to settle the aircraft in the runway and ensure this landing brake. But we can land with the spoilers disarm, which is a absolutely non-standard procedure. In this case, once landing, the pilot will need to select one of the two thrust levers on the reverse range just to deploy these spoiler surfaces. Well, we have this partial extension function on the ground for the ground spoiler control, and this function basically refers to, well, the ground spoiler partially extend when the reverse is selecting one of the at least one engine. This is basically for this partial spoiler extension is just to settle, to make the aircraft settle down on the runway, and then make easier this braking function during the landing roll. This partial extension by decreasing the lift eases the compression of the second main landing gear strut. Retraction. How can we retract the spoilers? Well, usually the ground spoiler retract after landing. Once we vacate the runway, the pilot line will push the thrust, push the spoiler lever down, and the spoiler will disarm, will deploy, will retract in this case. Well, in case of after re-entry takeoff, remember always that once we have brought the airplane to fully stop, and we apply the e-connections, call to the cabin crew, all the standard procedures. If we need to move back again from that position, we will need to disarm the spoilers. Otherwise, the spoilers will keep fully extended. Well, during a touch and go, when at least one thrust lever is advanced above 20 degrees, well, in that case, the spoiler will automatically retract as well. We have in this picture this how the spoilers works during the landing roll or during the re-entry takeoff. And remember that for this, in case of re-entry takeoff, abandoned takeoff, these spoilers will deploy as soon as our speed is above 72 knots. And these spoiler deployment extensions will send the electrical sign for the auto brake activation. You will see during the A320 course, GTA, you will see that we have basically two braking modes for the auto brake, low or medium. So if we selected low mode, the auto brake will commence the braking function. That's just 4 seconds after this spoiler's deployment. If we select auto brake medium, the auto brake will commence the braking function just 2 seconds after this spoiler's deployment. Well, now we're entering in, this is quite interesting part of this flight control chapter, which is Airbus normal low. This normal low, which is the standard low, that this is when in the node that we are flying, we are working in during the normal condition without no failures, no abnormal situation, no malfunctions in the airplane. So we are working and flying under this normal low. This normal low covers the full 3-axis control. We will have available some flight envelope protection, which is great, it's good. And we'll talk about this later more in depth during the next slides. And we have as well, which is called elevation of maneuver loads. Normal low, alternate, and direct loads are themselves divided in 3 modes, depending on the flight phase. We are on ground mode during ground operations. As soon as we are getting airborne after the liftoff, we enter in flight mode. And as soon as we pass 50 feet during the landing and 30 feet, we enter in this flare mode. Well, additionally, depending on the failures that we are getting, we'll talk about normal low, alternate load, direct load, and we'll talk as well about mechanical backup and abnormal attitude load, which is another 2 loads, another 2 flight loads, depending on how degradation we are getting due to these failures, due to these failures or malfunction on the A320 in flight. Well, normal low, pitch control ground mode. The ground mode is a direct relationship between the side stick deflection and the elevator deflection without auto trim. It makes a more natural feeling on the control during the takeoff and rotation. The THS is set at 0 degrees unless the crew has selected manually for other takeoff value. We usually do that. We set the THS in a specific value depending on our center of gravity before takeoff. When the aircraft reaches 75 knots during takeoff roll, the system reduces the maximum pitch up elevator deflection to 30 to 20 degrees. And well, regarding the pitch control once in flight mode, the flight mode is a low factor demand mode, which automatically trim and protection through the flight envelope. Well, so when we are, next point makes this concept quite clear. With the side stick movements, pilot requests a pitch rate instead of elevator surface deflection as a conventional aircraft. And this is one of the key points of the fly-by-wire system. So when we are in flight, when the pilot applies a side stick input, what we are doing as a pilot is requesting or demanding this pitch rate. We are not moving the elevator surface as we used to do it on the previous airplane or conventional aircraft. The pitch trim is automatic both in manual and when the autopilot is engaged. And during normal turns up to 33 of bank, the pilot does not have to make any pitch trim corrections. We'll talk about this on the bank angle protection. So we are during our takeoff roll, and we are at this point. Side stick is released. So after rotation, during rotation, we'll put the side stick back. Once we get airborne, we release our side stick and we will get pitch auto trim. And now we are during initial climb phase. Then we need to level up, for example, at 5,000 feet. So we will apply side stick input forward. And in this case, when we reach the 5,000 feet, we will release the side stick and we will get the auto trim function with the side stick in the neutral position. So once again, what we are doing is just when we apply side stick input, we are applying load factor or in this case, roll or pitch rate. We are not deflecting we are not deflecting directly the elevator, I mean the flight control surface. Well, normal low lateral control on ground when the aircraft is on ground, the side stick commands the aileron and roll spoiler deflection. The amount of this deflection depends on the aircraft speed. The pedals control rudder deflection through mechanical linkage, as we discussed on the first part of this presentation. And once we are in flight on the lateral control flight mode, the aircraft smoothly transitions to flight mode shortly after liftoff. The pilot has to control the roll and heading, but also limits the roll rate and bank angle, coordinate the turns and yaw damp, as we discussed on the yaw rate, on the yaw functions on the rudder. Well, what will happen during the flare in lateral control in flare mode? The lateral control is the same as flight mode, and once after touchdown, the aircraft smoothly transitions from flight mode to this ground mode. Well, now we are getting into the how is the our normal low, which protections do we have on the A320 thanks to the this fly-by-wire system? Well, during normal condition, in normal low, we will have low factor limitation. The system will limit, even if the pilot apply an abrupt side stick input, our low factor will be limited to -1 G and +2.5 Gs for clean configuration, or 0 Gs and +2 Gs for other configuration on the flap, depending on the flap setting. Well, pitch attitude protections, once again, even if the pilot pull side stick fully back and apply abrupt side stick input, the system will limit this input just to keep the airplane flying in the safe flight envelope. So our maximum, during normal low, our maximum nose up pitch attitude is 30 degrees if we are in configuration 023, or 25 degrees nose up if we are under configuration with flaps full. 15 degrees for nose down. Well, the flight director's bars disappear when PFD primary flight director if pitch exceeds from +25 or -13. You will practice on the type rating course some maneuvers. For example, memory items. You will practice what will happen when you are under ground proximity warning system, when the system will give the indication, the warning of pull up, and these memory items states autopilot off, side stick full back, toggle thrust selected, winch level, check that the landing gear is up and the speed brake is retracted. So you will see on the simulator.
David, excuse me, the diapo is in blank. Can you do anything just to? Okay, now it's okay.
Now it's okay.
Now it's okay. Thank you. Sorry.
Okay. Thank you, Fernando. Thanks a lot. So, well, so I will brief again this slide, which is quite important. We have during normal low potential, low factor, -1 G to +2.5 in case of clean configuration, or 0 +2 in case of other configuration. Pitch attitude protection, which is 30 degrees nose up in configuration 0 to 3, or 25 nose up maximum if we are in config full, and then 15 nose down in case for the nose down maximum pitch attitude. Well, as I was saying, you will practice on the same in case of this memory item, ground proximity warning system. When you disconnect autopilot and you apply side stick back full deflection, you will see that the flight director bars will disappear as soon as you pass this 25 degrees nose up. Well, more protections that we have on the normal low. We have the high speed protection. This protection is activated at or above VMO or MMO, depending on the corrections. When activated, the THS setting is a limit between the setting and the aircraft entry into this protection at 11 degrees nose up. With the side stick release, the aircraft returns to a band angle of 0. And as the speed increases, the side stick nose down authority is progressively reduced, and a permanent nose up order is applied to air recovery. So even when this high speed protection is active, even if the pilot is applying full forward side stick input, you will notice how the airplane is taking your nose up just to keep you outside of this, out of this overspeed protection. The high-speed protection is activated when the speed decreases below VMO or MMO, and normal controls loads are recovered. Autopilot disconnect when the high-speed protection becomes active. Well, how is this all this? How does this high-speed protection work? Well, there is some slight differences depending on which A320 you are flying, depending on the software, on the flight control computer software. For the A320 Neo, for the latest version, this high-speed protection works. Well, imagine that we are flying at flight level 380, and suddenly we are getting a strong tailwind, or then suddenly the tailwind changed from 50 knots tailwind to 100 knots headwind. Well, when we are approaching to the VMO, MMO, to the red color strip, the autothrust, the first step is that the autothrust will reduce power just to avoid entering in this area. If our indicated airspeed is still increasing and entering the red strip bar, the next thing that will happen is that as soon as we reach the green dashes indication, we'll get the ding, ding, ding aural warning and the master warning red light, which means that we have exceeded this overspeed, this speed limit. Next thing that will happen if we are still increasing our indicated airspeed, as soon as we reach VMO plus 15, plus 15 knots, the autopilot drops. And as soon as when we reach VMO plus 16 knots, we'll notice this nose up attitude, nose up, pitch up movement, even if the pilot is applying full forward side stick deployment. This is the A320 Neo software protection regarding this high-speed protection. Well, bank angle protection, this is quite important as well. During normal load, well, inside the normal flight envelope, the system maintains positive stability for bank angles above 33. If the pilot releases the side stick at a bank angle greater than 33, the bank angle automatically reduces to 33. So if we apply side stick lateral deflection up to 33, and we release the side stick, the airplane will keep turning with those 20 degrees or 25 degrees or 30 degrees bank angle turn. But if we increase our lateral deflection over 33, so for example, say that we increase our side stick deflection up to 45 degrees, and then we release the side stick, the bank angle will turn back to 33 degrees. Well, if the pilot holds full lateral side stick deflection, the bank angle will go to 67 degrees and no further. So under this normal bank angle protection, even if the pilot applies full lateral side stick deflection, the bank angle will reach bank angle deflection 67 degrees and no more than that. Well, what will happen when we are under both protections at the same time? Angle of attack protection is active and the pilot maintains full lateral side stick. In this case, the bank angle is limited to 45 degrees instead of 67. And the same for high-speed protection. If we are in high-speed protection and we apply lateral side stick input maximum deflection, the lateral bank angle will be limited to 40 degrees instead of 67. Well, when bank angle protection is active, auto trim is inoperative. And if the bank angle exceeds 45 degrees, the autopilot disconnect and the flight director bars disappear. This is quite interesting as well. You will practice on the simulator during the full flight sim sessions. When we are flying manually and we apply lateral side stick deflection more than 45 degrees, you will notice, you will see that the flight director bars disappears, and then we'll get back again as soon as we are reducing our bank angle below 40 degrees. Well, this graphic is quite good. It's quite schematic. It's quite just to make this concept clear. And basically what we have here is during up to 33 degrees bank angle, which is in the green range, we will have pitch auto trim. And remember that if we release the side stick, which is this range, the airplane will keep turning with those with this bank angle turn. Well, if we apply side stick deflection over 33 degrees and up to 67, if the pilot releases the side stick, remember that this bank angle will turn back to 33 degrees and will stay there. And well, this is how basically how this system works. We do have this turn coordination over the whole range from 0 to 67 degrees. Well, high angle of attack rotation. This is quite important as well. We will have this rotation during a normal load. Basically, this is if we take a look to the to our PFD speed scale. In this normal low, we find VLS, which is the lowest selectable speed stall. And then we have the yellow strip, which is V alpha approach, and the red strip, which is V alpha max. Well, this rotation and the normal low, when the angle of attack becomes greater than the alpha approach, the system switches the elevator control from normal low to a protection mode, in which from alpha approach to alpha max, the side stick commands alpha directly. So we discussed on the previous slide that our pitch rate, the pilot, when apply pitch input in the side stick, what we are doing is demanding pitch rate or load factor. Well, in this case, when we are between alpha approach and alpha max, what we are doing with the side stick is just well, the elevator switches from normal to a protection mode, and we are demanding in this case alpha degrees directly. So the angle of attack will not exceed alpha max, even if the pilot applies side stick full back. So if we are in V alpha approach in the yellow strip, and the pilot applies side stick full back deflection, we will turn into the red color, into the red V alpha max, and the system, the alpha 4 protection will activate, and we will not allow to the pilot going beyond this red max. Then, if the pilot release side stick, the system, this angle of attack rotation, will take the nose down, and we will change from alpha max from the red strip to alpha approach to the yellow strip, and we will stay there. This is how basically this high angle of attack rotation work. The autopilot will disconnect, of course, when this alpha angle of attack rotation gets active. Well, in this slide, we will talk about what's side slip target. In this case, we have in our PFD, in our primary flight display, this trapezoidal index, which will be moving beneath the roll index. Well, on ground, it represents the lateral acceleration on the airplane, on the aircraft, but in flight, this side slip target, which is usually in yellow color, it will change to blue color, cyan color, which is what's going on in there. Why this trapezoidal shape will change in the blue color? Basically, the FAC, the flight augmentation computer, is moving this part just to give an idea to the pilot which rudder the pilot has to apply just to remove this yaw moment and keep the aircraft well centered on the runway or in flight center line. We usually get this side slip in case of engine failure during takeoff, or in case of go around with single engine. We are doing single engine go around. So this side slip target will change to blue color if we are in configuration 1, 2, 3. And any of the engines N1 is above 80%, or one thrust lever is above MCT, maximum continuous thrust, or when the difference between engine N1s exceeds more than 35%. In this case, we'll get this side slip side slip indication, which is, as I said, is the fact the flight implementation computer is giving the pilot an idea which rudder has to apply to remove this yaw moment. Well, flight control reconfiguration laws, depending on the failures that we are getting in flight, which system we are losing, which failures or malfunction, will turn from the normal load to alternate load, direct mechanical backup, or abnormal attitude. Well, alternate load, we basically have the load factor limitation protection, which is basically the same as normal load. We don't have any pitch attitude protections. We don't have any high angle of attack protection, but we have something similar to the high angle of attack protection, which is called low speed stability. It's an artificial low speed stability replaces this normal angle of attack protection. And the pilot will notice a progressive nose down signal, which is introduced, which tends to keep the speed from falling below these values. The difference is that the pilot can override this demand. I mean, in this alternate low, if we get into this low speed stability, if the pilot pulls a stick back again fully deployed, we will enter, in this case, we will enter in a stall condition. So be careful with that. We still have audio stall warnings, and the PFD scale is modified as we will see in the next slide. So do we have, the question is, do we have alpha flow protection in alternate low? No, we don't. What we have is something similar, which is called low speed stability. Well, we have an alternate high speed stability above VMO or MMO. A nose up demand is introduced just to avoid entering this overspeed. And once again, the pilot can override this demand. So if the pilot keeps pushing IST full forward, we will enter in this overspeed condition. And there is no bank angle protection in alternate low. Well, what will happen if we are still increasing and we are getting more malfunctions or more degradation in our systems? For example, you will practice on the entire rating course that we lose both flight augmentation computers, FAC1 and FAC2. You will see that you will enter in alternate low, and during the approach into land, as soon as you take the gear down, you will change from alternate low into direct low. In this case, in direct low, the pitch control is a direct stick to elevator relationship. So you will notice that the airplane is quite more sensitive to the side stick movements. The maximum elevator deflection varies with the center of gravity. There is no automatic pitch trim, so the pilot has to use during the approach to land, will use the trim wheels, since there is no automatic trim. And you will get on your PFD indication, the top part, you will get use manual pitch trim in yellow color, which is indication that you are flying under direct load. No protections are operative, and we still have overspeed and stall warnings available. The lateral control is direct stick relationship as well, and you will notice that it is, as I mentioned, is quite more sensitive. Well, this is the direct low indications that we will have in our PFD. As you can see, we have this use manual pitch trim in yellow core indications. And in this case, we have these amber crosses, which is saying, okay, be careful because you don't have any bank angle protections, and be careful because we don't have any nose up or nose down limit protections. Well, this slide is quite, I like this slide since it gives a general idea about which indication we'll get in our PFD depending on the lows that we are flying in. So in normal low, we have this indication that this green dashes, which is giving us indication of how much nose down, remember it's 15 degrees, and how much nose up we are limited to 30 degrees with config 0, 1, 2, and 3, and 25 with config full. Then we have the bank angle limitation, which is green dashes up to 67. But in alternate low, now we have these amber dashes, amber crosses. And if we are under direct load, now we will get, in this case, use manual pitch train and the amber crosses, which is giving indication to the pilot, okay, heads up, be careful, because in this case, alternate or direct load, you are not, well, you are flying under no protections. Another good indication is in our speed indication. In case of normal load, we will have BLS, B alpha prot, and B alpha max. But when we turn into alternate load or direct load, the speed PFD indication, now we will get only BLS, which is the lowest selectable stall speed, and BSW, which is, well, that's a stall warning speed. So, which is quite different from the PFD on a normal load. Well, mechanical backup. As soon as if we lose all the flight control computers, we'll get into the mechanical backup. In this case, we'll get manual pitch string, a red color on the top part of the PFD. And now, well, this mechanical backup low is designed just to keep the airplane safely in flight in a safe conditions. But remember, it's not a flight low design for landing. Just to keep the airplane safe in flight, go with the ACAN troubleshooting, go with the QRH, a quick reference handbook, check the FCON, do all the abnormal procedures, and try to revert this flight control low from mechanical backup to direct or alternate low or normal low, and now we will be able to perform a safe approach and landing. Well, the main reason why this flight low is not designed for landing is because the pitch movement that the pilot will have available only is the trim wheels, and the lateral movement that we will have as a pilot available is only the rudder's movement. So you can imagine how difficult it is to perform a safe landing when we are flying in mechanical backup low. We will practice on the type rating course at GTA in the last FFS last scene session, just for you to know how difficult it is to perform and figure out that this mechanical backup flight load is not designed for approach and landing. Well, additionally, we have in flight, not in the sim. There is no sim in the world that can simulate this abnormal altitude load, which is basically if we are in a real flight and the pilot performs a side stick input and abrupt and aggressive side stick input. I don't know, depending which situations can we find in flight for this abrupt side stick input, for example, mid-air collision or collision with the ground, and the pilot side stick full back condition, the airplane might enter in this abnormal attitude. Basically, this abnormal attitude will get active when the pilot, as a big numbers, when the pilot applies this side stick abrupt input, and we are requesting to the flight warning to the flight control surfaces flight input more than double than the limitation. I mean, a bank angle above 125. Remember that the bank angle limitation was 67. We are requesting or demanding a pitch attitude above 50 degrees nose up or below -30. Remember that the limitations for the pitch up was 30 or 25, and for the nose down -15. And same for speeds below 60 and 90 Mach above. So as you can see, this is definitely non-standard flight condition and completely out of the flight envelope. Well, this is just to give you an idea before joining to the type rating course. How is the how are our indications? Well, the control indication for the pedestal, as we discussed, for the ground spoiler are on the sun on the speed brake level. We have talked about the rudder trim. Remember that we will use this rudder trim in case of engine failure or one engine out go around. Which indications we will have in normal flight with no failures. This rudder trim indication in flight, say flight level 370, normal speed Mach 0.77 or 0.78, wings level, no failures this indication, this rudder trim indication, should be between 1.0 right and 2.3 left, which means that the actual rudder deflection is plus minus 1.5 degrees. If this indication is beyond this limit, I mean beyond 1 right or 2.3 left, we should, once after landing, we should call for maintenance engineers just to make a rudder inspection. How is this flight control surface? You will find this data on the Airbus manual, the FCON system flight control rudder trimming function. Well, this is, as I discussed, this is the pitch string wheels that we will move this string on ground depending on how is our center of gravity. While side stick with autopilot disconnection, radio PGT, overhead panels, we do have 7 flight control surfaces, 7 flight control computers, FAC1, SEC1, ELAC2, FAC2, SEC2, and SEC3, ELAC1. But remember that on the flight control ECAM page, we have only 5 flight control computers indication, not 7. Well, side stick indication on the PFD, which this side stick deflection indication will get this white cross as soon as we have one engine starting, and this cross will disappear as soon as we get airborne after lift off. While flight control page indication and the ECAN will get more in depth unit type rating course. We have spoilers in the deflection indication as well in our ECAN wheel page, just giving a pilot which indication about which spoilers are deployed at that time. And this is last but not least, the last slide. Just to give you as a summary, quick summary, big picture about how does a fly-by-wire system works on the A320. So roughly, well, key point on the fly-by-wire system is that the pilot will apply side stick input. This side stick input will travel to the 7 flight control computers. Those computers will evaluate if this pilot input it's within the safe flight envelope, and then this input will travel to the servo jacks, hydraulic actuators, and will deploy the surface just to keep the airplane within the safe flight envelope. Well, this is all from my side. I hope you have recalled and you have get a big picture, big idea about how the flight control system works on the A320, what's a fly-by-wire system. That's pretty much everything. Thanks a lot for watching. Stay safe during these days, and see you on the next presentation, on the next videos on this A320 jet orientation course in Global Training Aviation. Thanks a lot and stay safe. Bye-bye.